In this video, I am going to show you how to solve a relative motion problem. So this is a common exercise in physics. Let's take a look at what we have. So first, we begin by drawing a picture. Say you have a lake, and there's a little boat. So I'm drawing a top view of our little boat. And when the water is still, the boat can travel at 8 kilometers per hour. So when the water is still, the boat can travel at 8 kilometers per hour. Now, if you take this boat, so let's label this, so we see that this is the one that is the lake. Now imagine you take this boat and you place it in a river. And in this river, say the river is flowing this way. Okay, let's say this is the velocity of the river to the right. The boat can travel at a speed of 8 kilometers per hour relative to the water. Okay, so this velocity is 8 kilometers per hour relative to the water. So not relative to a person standing on the shore. Right, so here's a person standing on the shore like this, right? But relative to the water, this boat can travel 8 kilometers per hour. So let's answer some fundamental questions about relative motion. If we could, within this river, freeze the water and stop it from moving, then the boat would move at simply 8 kilometers per hour. So that means this person here would measure the boat at that speed. Okay, so part A of the question might be, if the water could be stopped so that its velocity is 0, what would be the speed of the boat relative to an observer on the shore? What would the person standing on the shore measure as the speed of the boat? So if that were the question, that would be, you would answer as 8 kilometers per hour. Okay, so this is as if water stops flowing, so to speak, okay, if you could achieve this. However, the next question might be, what if the water now is itself flowing at 3 kilometers per hour? Okay. I will use two different colors. Let this one here represent the 8 kilometers per hour of the boat, and then I draw a little green arrow, a green vector that represents the velocity of the water, and that is 3 kilometers per hour. So that looks like this. So what is the effective velocity of the boat relative to a person standing on a bank of the river? Well, in this case, you just add the velocity vectors. So what you do is you take the green arrow, which is the velocity of the water, and to it you would add the orange arrow, which is the velocity of the boat relative to the water. So this is your 3 kilometers per hour, and you're adding to it the 8 kilometers per hour like this. So the resultant velocity, as you can tell in this exercise, is the sum of these two. So you draw one arrow, that's 1, 2, 3, 4, 5, 6, 7. Okay? And this is the resultant velocity. And the magnitude of this velocity, of course, is 11 kilometers per hour, like this, okay? So what this tells us is the following. If you have a person standing on the shore, as this guy is doing, and he observes a boat going by, and this boat is moving and the water is moving at the same time, then relative to him, the boat moves at 11 kilometers per hour. And so if he could see the boat for a very great distance, right? And imagine this is his wristwatch and it's 12. Then 1 hour later, you see over here, not 1 o'clock, this boat, relative to him, has moved 11 kilometers. In other words, it's 11 kilometers downstream from this guy. Another type of question in this context is, what if the boat is moving upstream against the current? What is the effective velocity relative to an observer on a bank of the river? So how do we answer that question? That's the same as subtracting these vectors here. Okay? So what we mean is this. Take your boat, say it's traveling now. What are they telling us here? Okay. So this is, remember now, downstream means in the same direction. So if the boat and the river are moving in the same direction, then we describe that as motion downstream. Upstream means against the current, against the motion of the river, against the direction of the river. Okay? So I will actually, to illustrate that, draw a new picture. Okay, so it's clear. So imagine once again the river is flowing. 1, 2. Okay, so I've exaggerated the length of the arrow here, but it really means 3. Okay, so that's the velocity of the river here, 3 kilometers per hour, which remember means if I drop a little leaf into the river, and if I could see for a great distance, then 1 hour later, that leaf would be 3 kilometers downstream. Okay, if it's simply carried by the water. That's how far it would move in 1 hour. And now we have a boat in this water, and this boat points in this direction. Okay? And the velocity of the boat is 8. Okay, but in the opposite direction, so to speak. So we have 8 kilometers per hour, but upstream rather than downstream. So it looks like if this is our 3, then an 8 would be 1, 2, 3, 4, 5, 6, 7, 8. Right? This would be like the velocity of the boat upstream. This is the velocity of the water. And now the question is, what is the resultant? Okay, well, in other words, what's the effective velocity of the boat relative to somebody standing on the shore? They're on the bank of the river. Okay. What does this person measure as the velocity of the boat? So the way to do it is to use vector addition. These are velocities, they are vectors. So let's reproduce this long orange arrow, that velocity. That's 1, 2, 3, 4, 5, 6, 7, 8. Okay, roughly. Then you add to the green one, but it points in the opposite direction. So you place it here and then you go back 3. So 1, 2, 3. There you are. And then the effective velocity of the boat is what remains between them, which is this vector right here. Okay. So if this is 8 kilometers per hour, we will take upstream as negative. Right? So it's negative 8 kilometers per hour. Downstream we will take as positive, so that's positive 3 kilometers per hour. So when we add these two, what we obtain is the following. Negative 8 plus 3 is negative 5, so negative 5 kilometers per hour. So the effective velocity of the boat relative to the blue dude on the bank of the river here is 5 kilometers per hour negative, which means the same thing as upstream. Okay. So that means if he could see for a great distance, and if he watched the boat, 1 hour later it would be 5 kilometers from him against the current, okay, or upstream. And another common question is, we'll call this part D. If the water is flowing at 3 kilometers per hour downstream, like this, so let's use a vector to represent that velocity. Let's say this is our 3 here. Then how fast should the boat move so that its velocity relative to an observer on the shore is 0? Well, take a look. We'll again use an orange color, okay? If I want the effective velocity to be 0, then if the water is going down 3 kilometers per hour downstream at that rate, then the velocity of the boat relative to it must be 3 kilometers per hour upstream. You see? Then these two velocities cancel, and in that case, so this would be like negative 3 kilometers per hour. Okay, so positive means downstream, negative means upstream. So this is like a negative 3 kilometers per hour upstream. Okay, when you add these two velocities, they cancel, and all that remains is an effective velocity of 0 meters per hour, or kilometers per hour. So in other words, an observer would see the boat stationary. If the water is flowing at 5 down and the boat is moving at 5 upstream, then to somebody on the shore, the effective velocity is 0. Okay, the boat appears not to move at all. Okay. Now, can we understand this concept a little more deeply? Because relative motion is a fairly difficult concept when you first encounter it. Let's take a look at another example. It might be of some use. Okay. Imagine you are on a belt at an airport, okay? So you get into a belt and it moves you down a long hallway to speed up the process of, to improve traffic flow, and the flow of people through all the long hallways that they have at airports. Now, if you have the following situation, okay? Let's say this is a side view. This is like a roller, and then the belt is wrapped around the rollers, see? Let's say the roller here, right? If I fix the position on the roller, let's say that can move at 1 meter per 1 second, for example. So it's fairly brisk, okay? So 1 second later, this point here has moved, and it's now located over here. And then another second later, this point has moved again, and it's now located over here. If you are on this belt and you don't want to move, you want to appear to be stationary to somebody who's on a carpet and is not actually on the belt as you are, then you simply have to walk at the same rate but in the opposite direction, which means every time this point, okay, takes a step, so to speak, you take a step in that opposite direction, which means that the effective motion is nothing. Whatever the belt does, you undo by taking a step, okay, in the opposite direction at the same rate of 1 meter per 1 second, which means then the effective motion you have relative to somebody on the carpet nearby is zero. You simply appear to be stationary. And if you're not convinced, just go to an airport, get on one of those belts, okay? Find, adjust yourself until you see how fast it's moving. Start moving at the same rate in the opposite direction, and you will see you will end up not moving at all, relative to somebody who's on the carpet and is looking at you in the belt. Okay? There you go. So thank you for watching.